Hello everyone, and today in this session I'll just briefly explain about the research software engineering team that's in the research computing facility that Phil introduced right at the start. Just to give an outline of what I'll be talking about, it's really to give some background on what is research software engineering that we do, what are we as a team doing that, and how do we contribute to research that's been done in the college, and how can we possibly help other people in the future. So at a very quick level, high level, what our team is intending to do, it's trying to enhance MVLS research output by essentially by three things there. Trying to develop high quality and robust research software, and improving the skills of people within the college and wider, and also looking at developing and coordinating a community of practice around research software. So to really explain what some of that means, we'll probably have to explain what do we mean by research software, and also then what is research software engineering. So software is used quite widely in research, both in college and much more widely. And so, for example, we can use software in research to be capturing, visualizing, and presenting data that is part of our research. We can then be using software in the modeling that's being done, and that can be computational, methodological, mechanistic, and statistical modeling. We can just be processing images. So we might have brain scans, we might have images of fields and so on, and we can analyze those. Machine learning, obviously, that's using software to do that. And while we're talking about research software, software is also used in sort of dissemination of research outputs and in clinical settings as well. So very broadly, the techniques we'll be talking about and the support we'll be offering can apply much more widely than just in pure research settings. So knowing what research software is, what can we say what's research software engineering? So research software engineering is really about applying the more general principles of software engineering to research software that we're generating. And so a lot of the concerns we have are going to be the same concerns that we have for research more generally. Are the results that we're generating from our research software correct? Can the results we've generated be trusted by others, and can they be reproduced? If part of the software development we're generating a tool, is this a tool that other people can easily use or adapt for their own purposes? Is it contributing to essentially more general research output? And if we have, again, a tool, is it efficient, secure, and sustainable in some meaningful way? So it's about good practice in software development to make research as good as it can be. So let's look at a specific example. So if we have an epidemiological model, something that looks like an SIR model that many people would have seen and certainly has come to quite a lot of prominence over the recent years. So if we have a research question, given an epidemiological model like this with some constraints, some assumptions, how many infections do we see over time? And we can generate a piece of software that can answer this question for us in some meaningful way. And so, for example, one example of a tool that can do that is I've got a nice little bit of code there. I run that code and I get a nice pretty graph that comes out at the end of it. And that's telling me over time, what is the count of infections? So I can change the numbers in there. There's a model assumptions parameterization. I can change those. There's some numbers here and here. I can change those and I get a different shape graph. But this isn't really a very useful tool for many people. How can we develop that? So we're going to care about, as a useful tool, can we assure the quality and usability of that tool? So do we have testing? Do we have documentation? Is the code we presented readable and maintainable? And can we check how changes go through, that they modify things? Can we roll back and see how things have modified? And if we introduce a mistake, can we find that mistake? And that tool I gave you there didn't meet any of those boxes at all, realistically. Also, we look at, is the tool we've generated portable and reproducible? Can we manage data? Do we have metadata describing what we've done? Can we generate pipelines which make sure that we can have input assumptions tracking all the way through output, looking at provenance tracking for the input and output for our models? Do we have versioning for the input and output data and the source code as well? When we're publishing the results in this and we make a version 2 of this, can we show that version 1 was used for the paper and it's this is now version 2? Can we go back and reproduce what we published? And all this is contributing to open research. And we want to possibly consider the findable, accessible, interoperable, and reproducible considerations of FAIR, both in data and software. So we've spoken very quickly there about some of the examples for that particular tool we could consider. So within the research software engineering community, Neil Chu Hong a couple of years ago talked about the concept of research software development principles. And he generated 9 principles, and there's a link at the bottom there for a keynote presentation he gave at a community conference about this. So making sure we can develop software that in our research helps the team, helps the peers, and help the world. And the RSE team is able to put these principles to the support of coding that we might be doing for you. So I've given you a toy example. Let's look at some real world examples that the RSE team has contributed to within the college's outputs for science. So with colleagues in cardiovascular metabolic health, they're looking at implantable tools and the visualization of results from medical measurements, clinical measurements there. So supporting end-to-end software components, looking at data ingestion and visualization analysis of that. Through, again, this idea of the FAIR, the findable, accessible, interoperable, and reproducible, traceable data, looking at introducing a pipeline to make it easier for scientists to be able to share their data sets. And so the tool that's been contributed to, or this FAIR data pipeline. Within the infection immunity schools, the team has been contributing to a couple of visualization tools, images here around single cell analysis, a web interface for that, the code being accessible there, and RSE within that, sort of looking at code development, reviewing papers, maintaining servers, and so on. Another example of this is the Apollo 3, a genome annotation editor as a plugin, so people can annotate their genomes doing that. So benefits of a central team to contribute towards the software development. Software development can happen within your research groups. It does happen within your research groups. What can a team such as the one in SRF provide on top of that work? So we're looking at the scale, breadth, and reduction of duplication of effort on that. So we have a pool of staff model. So essentially, you can access highly qualified and competent RSE support for short or sporadic durations. We can also provide the peer and management support for staff within the research groups. And we're also able to retain highly specialized skills that aren't tied to project funding. So we retain an institutional memory. We can provide long-term support through posts that are underwritten by college funding rather than going hand to mouth for research grants. And we're also able to integrate with other services in the college and the university. So at a very high level, we can contribute to software development. We're also interested in providing support for training, so the community, and providing more widespread advice as well, helping people do their own work as well as providing some input to software development as well. A little bit of detail as to what those are. So again, with software development, we can contribute staff time on that. We can contribute to defining what a research artifact looks like, providing advice on best practice on how to do that, providing code review. So you've got work, can you do the assurance on that? Engaging with the community and providing training as well to make sure that people are well placed to contribute research software roles within their research groups. So we're interested in providing the pre-application support. And there's a quote from a recently published paper, which did involve quite a bit of RSE effort, and saying that involvement from a research software engineer from the beginning could help ensure that best practices become routine from the start, rather than something to be adopted later. And so as part of that, we can be looking at providing prototypes or proof of concepts, and a few examples on the right. They're looking at some modelling, just proof of concept that can go into the research grant to show that the software engineering support can provide something useful for the funder. Code review, there we can say, at any stage of the project, we can provide a review to help promote good practice. So that could be looking at, you just want to get something ready for publication, or where is the development going on this? What aspects need to be considered before the assurance of the results can be taken? So very quickly to acknowledge who the team is. So out of the team there, we've got 3 research software engineers who can work on that. That's Ryan, Adrian and Will. And then on the right, just to thank those people who've allowed references to the work as part of the showcase there. Contact details on the bottom, along with a link to the research computing facility. Okay, thanks very much.